Hello, my name is Khalid Mohammed. This summer I worked at Space Telescope Science Institute with Dr. Scott Fleming, and we worked on searching for single transit events in TESS Lightcurves using machine learning. So first, let's talk about TESS. TESS is a space telescope. It stands for the Transiting Exoplanet Survey. It's NASA's newest planet hunting telescope, and it looks in the nearby galaxy to find exoplanets using the transit method. You can see in the top right this animation here of how the transit method works. The way it works is you monitor a star over time, measuring its intensity repeatedly, or periodically, I should say. And as a planet goes in front of the star, it'll obscure some of that light. So the intensity that you measure will decrease as a function of time. And then once it leaves the front of the star, the intensity will increase. And so this method allows us to find planets and also determine, given how that light curve looks, the parameters of that planet. TESS is able to measure the masses of planets with radii smaller than Earth and larger than Earth. And one of its primary missions is to find the best exoplanets for JWST to analyze, so we can find out what exoplanet atmospheres look like. The way TESS works is it has 4 CCDs aligned like this, one on top of each other. And if you imagine a sphere projected from Earth, it can view from 0 degrees around the galactic plane to about 90 degrees right above us. And over time, TESS will observe one sector of the sky for about 28 days, and then it'll rotate a bit and observe another sector of the sky for 28 days. And as it rotates, it's able to, over a period of about a year, view roughly the top hemisphere that we can observe. And then it'll flip over and do the same thing. And because of this geometry and where it's looking, there are actually some sectors of the sky that TESS will observe over a very long time, almost a year. And so there's a lot of data, there's a wealth of data that TESS has that we can look for planets through. And I just think this picture right here of TESS's first light is very pretty, so I wanted to show that. And just as an animation here, it's just for people who like visuals, this is how TESS observes our sky. So we have our 4 CCDs on top of each other, observing about 90 degrees, and then it'll rotate. Imaging at a cadence of, I believe, every 30 minutes with actual specific sectors of the CCD, the science team found interesting at a cadence of, I believe, 2 minutes, which I think is really cool. So I said in my title slide, we used machine learning. What's machine learning? Machine learning is a suite or class of algorithms that tries to answer a question and improve over time. Over time being like actual time, as well as the amount of data that we have. The goal that we have is to classify light curves as bearing a certain type of exoplanet or not. So we're using a classifier. The classifier we're using is called a random forest, and I'll talk about that later. To talk about our concrete science goal, we have all these light curves and we want to find exoplanets. So can we use a classifier, a machine learning classifier, to classify light curves as bearing a specific type of light curve that we care about? To do this, we use raw data, or more accurately, the data provided to us and pre-computed properties that we determine to classify these light curves. So you can just see here a map of different types of machine learning algorithms, and we're specifically focusing on classifiers. So what are our science goals? A team at MIT provided to us about 1 million calibrated light curves from these TESS images, and we're looking for long duration isolated transits. Now, TESS is really good at finding planets like hot Jupiters, which are really big and have periods of less than 10 days. Those are pretty easy to spot. The question then becomes, can we find planets with longer transit periods? So we want to find these planets that are not typically found during the mission's planet search. And these planets are scientifically valuable because they're very expensive, both in terms of observation and I guess computationally to find. And so these signals that we're looking for could be caused by long period transiting exoplanets. This isn't exactly a novel field. So here are 3 papers that I read and really enjoyed over the summer. The first one used a machine learning algorithm called a deep neural net, and it correctly identified light curves as having a planet 98.8% of the time. That was really interesting. These other two papers were similarly successful, and they used different methods. The one on the right, Offman et al., was really, really interesting because they were able to combine both an AI approach and a machine learning approach to rapidly plow through data to find and classify light curves as possessing exoplanets. So I find this a really cool field, and I'm really excited that I got to do this summer. So just to reiterate, what were our science goals? We wanted to identify the best target light curves, the best target systems, which might contain long period transits. And then our second goal was, hey, we found a transit. Can we quantify what the parameters are? What's the radius of this planet? What's the duration of the transit? What's the actual period? So our first method was filtering down our data set and then using a model of a light curve. So the data set we used was the TOI data set. TOI stands for TESS Objects of Interest. This is a collection of the most promising exoplanet candidates that TESS has found. And these data include the actual planet candidates, their parameters like radius, star temperature, gravity, etc. And then from there, we wanted to simplify our first goal, or what we're trying to do. So we looked at those systems which had host stars of 1.2 solar masses and single planet systems. Single planet systems because multi-planet systems are hard to work with. And then 1.2 solar masses are smaller because the smaller the star, the higher the proportion of the star the planet will obscure and the easier it'll be able to detect. And you can actually see the light curves to the right that we're working at like changes in intensity of less than 1%. And so we want to get those smaller stars so we can be able to better detect these planets. Secondly, the light curve model package we used was Batman. It simulates light curves given input parameters such as semi-major axis, how far the planet away is from the star, period, planet radius, etc. And then it estimates what the light curve should look like. So you can see here, for a target that's sort of like what we're looking for, we have a period of 9.7 days, and you can see that the light curve dips about 0.008%, and then it goes back up, and you can see the same thing to the far right simulated light curve. And so we can combine real data and an idealized transit from our model to see if we can find those long period transiting exoplanets. So the first thing we did over the summer was we built a pipeline that, if you wanted to apply a similar approach and use our pipeline, we can, take a desired set of transit and host parameters. Say you wanted big stars, like let's say A stars, you can tell us that and we'll retrieve that data for you and we'll get those light curves. From those light curves, we model every single target's light curve using the TOI parameters present in the data set. And then we also calculate pre-computed statistics we called metrics, which I'll talk about in a bit. Given these metrics, the TOI light curve and the modeled light curve, we pass this into our random forest classifier, which tries to identify, is a given light curve bearing an exoplanet or not? We used a random forest classifier, as I said earlier. The way it works is much like a real forest. It's composed of trees. These trees are called decision trees. Decision trees are a machine learning algorithm which I guess goes through a set of yes or no questions on the features of the data to construct a way of deciding whether a piece of data belongs to one class or another. You can use the same sort of method to estimate parameters. That's called regression, but that's not exactly what we wanted to start with. And so a random forest classifier, the idea behind it is you get a bunch of these decision trees and add some stochasticity, and I believe what data they're training on. And if you have a bunch of mediocre trees, if you aggregate them, you can imagine that they would perform better than one really good decision tree. In part because one really good decision tree usually overfits on the noise present in the data. And so we have this labeled input data from the TOI data set. We estimate how we can classify it. And then we can estimate, given other data, let's say other light curves, we can say, do we believe this light curve has a long period or just an exoplanet in it? And so that's one thing that we did. Now, with our actual metrics, you can pass in just your data and just your models into the random forest classifier, but it often behooves you to calculate pre-computed statistics. If you're familiar with the realm of, I guess, transit and periodicity, or I guess transit astronomy, you can imagine a statistic like a periodicity, how periodic is your light curve, would be a strong indicator whether or not you might have an exoplanet in your light curve. And so what we did was we gathered or wrote a set of pre-computed statistics we could get from our light curves. So we got the root mean square from our model and the data. We got skew and kurtosis from the light curves. We got dip and dip width, with dip being, is there a set of fluxes that are 3 sigma away from the median of the light curve? Because you would imagine that if they're 3 sigma away, they might be scientifically relevant enough to be considered worthwhile dip in the light curve to consider. And our width is how many fluxes in a row is that. And then we also consider our fluxes which error bars don't cross that 3 sigma threshold also present, because you'd imagine a flux with a high error wouldn't really be the best thing to factor in to your model. And we pass in other metrics there as well. And this is very modular code that we wrote. To the right, you can see an example of our metrics. We get the standard deviation of our light curves as well as the dip and dip width. And you can see that the TOIs in this given sector, so in this given image or imaging area that TESS observed, that those identified planets seem to have higher in the blue dip widths. So they have more consecutive fluxes below 3 sigma of the median. And then those which aren't identified as planets seem to have a much higher scatter and much fewer dips. So that's something to think about in what we factor into our machine learning model. And that's just an example right here of what we classify as a dip or a dip flux. So how did our random forest classifier perform? If you recall back to the papers we read, there were like percentage accuracies of like 98%, which I think is really cool and really stellar. And what we did to measure our success or quantify our success was just use the mean squared error, which you can think of as a proxy to accuracy. And so the mean squared error we had on our training data on synthetic and real light curves was about 0.04 or about 4%. So you can imagine that we had an accuracy of roughly 96%. And then on our actual testing data, when we applied it to other test data, we had a error of about 8%. So we had a accuracy of about 92%, which was pretty good. And just to reiterate, our mean square error represents the residual error of our classifier. In the future and this semester, we're exploring other ways to more rigorously quantify how well our machine learning algorithm worked on classifying light curves using other statistics such as recall, precision, and a confusion matrix, just so we can more accurately examine where our machine learning model succeeds and where it fails. But just to reiterate, we had an accuracy of about 92% on our test data and 96% on our training data. Now let's talk about our next steps. So we have a classifier that's able to tell you, does this light curve bear an exoplanet or not? The next question is, what does that exoplanet or that system look like? What's the radius of the planet? What's the period? What's the transit duration? It's a semi-major axis, etc. And in talking with the machine learning office at Space Telescope, one of the machine learning models we were thinking about applying in the future was a variable autoencoder. A variable autoencoder has 2 steps. It tries to encode and then decode data. By the first half, the encoder, it takes in your data and tries to reduce it into a set of latent parameters, or values that it thinks are meaningful in classifying or compressing your data. These latent parameters don't have to be physically meaningful. They're usually a combination of the features of your data in whatever way the algorithm thinks fits best. From there, once you've encoded your data, the decoder tries to recreate the data from those few set of latent parameters. And so you can imagine if you take that first part of the encoder, you take your data and compress it into a few latent variables. that you can then train a regressor on estimating what should a light curve from these latent parameters look like. So if you have this data set of TOIs, which have already been identified as having planets, and then you're able to compress them into a few variables, latent variables, and then train a regressor to estimate what the light curve should look like, you can imagine that you'd be able to reconstruct these light curves and then estimate what the parameters are. And so we were thinking about using this model to, from our classified light curves, estimate what the parameters look like, estimate what the planet radius is, for example. And then from there, our final goal in the future of this project is to hunt for planets, hunt for those long period transiting exoplanets that are present in the TESS QLP light curves. I'd like to thank my stellar mentor, Dr. Scott Fleming from Space Telescope. I'd like to thank Dr. Susan Malali and her student, Michael Kuntz, who were part of our time series analysis group that we worked with over the summer. I'd like to thank my NAC mentor from Space Telescope, Dr. Ivelina Momcheva, as well as the machine learning office people that I talked to, Dr. Michelle Tapaka and John Wu. And then I'd like to thank the SASP program coordinator, Carolyn Slavinsky, as well as my 2-point people at NAC, Lindell Von Schill and Tierra Candelaria, for having a really stellar summer program. Thank you.
The question I have is, how did you deal with eclipsing binaries? Because I know they can also have transits in their light curves. So did you make any attempts to distinguish an exoplanet transit from an eclipsing binary transit?
That's a great question. I would wager the answer is no, because I believe the data set we were working with is constituted only by planet transits. And so that isn't something that we factored in, given the constraints of our projects. We're just looking for 1.2 solar mass stars or smaller with just a single planet transit. So I don't think we worked with binary systems.
Okay. All right. Thank you.
I wanted to ask about the sort of, you know, if you get to the point where you can identify these isolated, you know, transits for long period planets, sort of how much can you actually do with them? Is the hope that eventually another transit will pop up and then you'll know what the orbital period is and be able to work out the distance? Or is there something you can figure out statistically from looking at a large sample, that even if you don't know the individual periods?
That's a great question. I guess the first thing I would like to stress is that we're not like 100% confident that these are planets, right? We can only we say that these are good candidates, right? Mm-hmm. From there, I would wager that you can conduct ground-based or other space-based follow-up observations at that sector of the sky to see if that transit that we believe is there occurs again at the period that we might estimate.
Okay.
I hope that answers your question.
Yeah, it does. Thanks.